Hi everyone, it's week 10 in Business 2220, and we're going to do some confidence interval calculations today. I've selected problem 8.21. I don't think it's really on page 320. It's where it used to be in the old book. It's now on page 324. And we have this machine. I don't know what it does. It doesn't really matter. And it turns out if you throw this catalyst in, some chemical, its output will increase. We'll get more stuff out of it, whatever the stuff is. Right now, the machine doesn't do any better than 750 pounds per hour, I guess. I don't know. And the question is, if we put this stuff in, what happens? Well, the sample that was taken was of size 5. They made 5 test runs to see what effect this this catalyst would have on the machine. And they measured a sample mean of 811 pounds. Well, that's good. That's a lot better than 750. But how confident can we be that this catalyst really does increase it to more than 750 pounds? Well, the other fact we have is that the sample standard deviation is 19.6. Now, we don't know what the true population standard deviation is, nor do we know what the mean is, really, the population mean. What we're trying to do is come up with an estimate of where the mean might be. Now, I've drawn the picture over here on the right-hand side of the screen, just so we have some reference. And we know that for a 95% confidence interval, which is what we're asked to do, that 95% of the values will fall plus or minus 2 standard deviations, 1.96 standard deviations from the mean, right? Well, that's the individual measurements. Now, what we're really interested in here is not the spread of individual measurements, but rather the average. Where is the average going to fall? And we have the formula I've shown here for the lower and the upper limits. The lower and upper limits is the formula we've come to know and love almost. It's equal to the mean value, the sample mean, x bar. And from that, we either subtract or add a factor made up of t alpha over 2 times the sample standard deviation s divided by the square root of n. And that gives us a range. Now, let's look at this formula in a little more detail. X bar, we know what that is. That's the average of the 5 measurements. But what's this t alpha over 2 stuff? Well, if you'd flipped your book, I didn't bother to scan it, but you flipped your book to the back of chapter 8 on page 339, you find this nice little tree, of decision tree, really. And we start with the first question: is the value of sigma, the standard deviation, known? Well, almost always, and certainly in this case, we don't. All we have is the sample standard deviation. We don't know the true population standard deviation, sigma. So we have to say no. Next, is the population normal? Well, yes, it is sort of. We're told it's sort of bell-shaped. Or even if we said no, is it mound-shaped with a single peak and not very skewed? Well, we're told, we don't know for fact, in truth, but we're told, yes, we can make those assumptions. So that says that we have to use the t, the student's t distribution, rather than the normal distribution. Now the student the t distribution is really the same thing as the normal, except it's a little broader. Because we don't know what the standard deviation really is of the population, we have to use something that's a little bit sloppier. We can't be quite as precise. But that's okay. We've got a table for that. It's on page 319. And all we have to know is what's this alpha business, this t, or really the alpha over 2. Well, let me work on that a little bit. First of all, we know that this 95% confidence interval here. Oh, one thing I wanted to point out before I move on to actually doing the calculations. Notice how the sample standard deviation s is modified by the square root of n. That makes, when we divide something, divide a value by something, we know that it gets smaller. Now n in this particular case is 5, and if you happen to wonder, the square root of 5 is around 2, a little better than 2. We can be more precise. It's equal to square root of 5 is actually 2.23, 2.24. Now, for a normal distribution, the red line I've drawn here is for two standard deviations. But really now we can divide the two sample standard deviations by the square root of n, and that gives us 0.89. So you can see that the range of possible values for the average is a little less than one sample standard deviation. So rather than having to spread ourselves out over 40 pounds plus or minus, we now can spread ourselves out over plus or minus 20. So we've got a 2-to-1 improvement simply by taking a sample of size 5. Now this is a preliminary estimate. We don't know for sure, but what we're 95% going to be 95% confident is that the average value of the output of this machine, if we use the catalyst, will be somewhere in this narrow range. Okay, let's get back to figuring out what T alpha over 2 is. First question, and what is alpha? Well, alpha is really the inverse of the confidence level of 95%. It's our unconfidence level, if you will. It's our uncertainty. So this is going to be equal to 1 minus 0.95 or 0.05. That's alpha. Now, why do we have to do alpha over 2? Well, here's the problem. If this is 95% in the middle, that leaves the 5%, and there are two tails involved, right? An upper tail and a lower tail. So we have to spread this 0.05 out across the two tails, and because we think this is a mound-shaped distribution, we can put half of it in the lower tail and half in the upper tail. So our alpha over 2 is going to be equal to our alpha value divided by 2. So we have some for each tail. Okay, now the question, what is T? Well, that we need page 319 for. If you'll flip there, you'll find that, and first thing is the number of degrees of freedom. How many ways can this variable wiggle, I guess you could say? Well, it's equal to n minus 1. Now, we're not going to get into why it's n minus 1. Some mathematician did this for us. We're practical business people and economists. We don't need the calculus derivation of that fact. Take it on faith that it's n minus 1. So go down the df column to 4, and then scan your eye across to the 0.025 column, and we find a value of 2.776. So I'm going to put that in here, 0.776. And now we can go up here and calculate these values. So it's going to be equal to x bar, which is 811. I don't type in numbers, minus the T alpha over 2, which is 2.776, times S, which is that value right there, 19.6 whatever, divided by the SQRT of 5. And we get 786.609. Let's do it for the upper limit. Same deal, 811, except it's plus T alpha over 2 times S divided by square root of, I could have put all those dollar signs in, couldn't I? But it's too much work. 835. So this range right here that I have in blue, if I were to put the true values in, ranges from 786 to 835 pounds. That tells us that we can be 95% confident that the average value, if we run this experiment of 5 samples many times, the average value will never be lower than 780. Well, never. It'll be 2.5% of the time it'll be lower than 786. So we're pretty confident. Excuse me, I got a cold. We can be pretty confident that we're okay. Pardon me again. Just for fun, let's say we wanted to be 99% confident. If you go down to the T.005 column, which would correspond to an alpha of 0.01, and go across from the 4, we get 4.604. Let's just plug that in and see what range that gives us. 604. That gives us a range from 770 to 851. A little broader, quite a bit broader, but still we're okay because we're greater than 750. Now, there's another problem here that I think is worth taking a look at. Do I have time? Now, I'm going to pause and come back on the B segment and just show you how we could turn this problem around and do it the other way. So come on, take a look at the B. It won't take very long at all.